Hi everyone, welcome back to KIG1015 Dynamics. In our preceding topics, we solved most of the problems dealing with the motions of particles through the use of the fundamentals Newton's second law equation of motions, F equal to ma. If we were given a particles act upon by force F, we could solve this equation for the accelerations A. Then, if we apply the principle of kinematics that we have learned earlier, we could determine the velocity, the position of the particle at any time instance from these accelerations A. Using the equation F equal to ma together with the principle of kinematics allow us to obtain additional methods of analysis for the kinetics of particles. This will give us two additional methods of analysis, the methods of work and energies, and the methods of impulse and momentums. So today, we will look into the work and energy methods and look into how we can use or make use of this method to solve a problem that involve the kinetics of particles. This is the outline of today's lectures. We will look into the work and energy methods and the impulse momentum methods and what are their advantages using these methods, where you can see that later on the determination of acceleration may not be needed or unnecessary. Of course, in our today's lectures, we will be focusing on the work and energy methods. We will be discussing the work of a force and the kinetic energy of particles based on the principle of work and energies. And also the application of this principle of work and energies to the solutions of engineering problems. The concept of power and efficiencies of a machines will be also introduced. And the concept of potential energy of a conservative force and the application of these principles of conservations of energies will be also discussed, and how it can be applied to various problems of practical interest. In the analysis of the kinetics of particles, sometimes we were not given the information of accelerations of the particles. In this particular case, probably the Newton's second laws is not that preferable. We have others so-called principles or methods which can be used to solve the kinetics of particles. Here we are referring to the energies and momentum methods. Take these two examples. The pogo sticks allowed the boys to change between the kinetics energies, potential energies from gravity, and the potential energy in the springs. So in these particular applications, we do not have the accelerations informations, right? So it's easier to represent or to solve these particular problems in terms of energy methods, or here to be exact, work energy methods. If you want to analyze those car accidents, usually it is analyzed by using impulse or momentum methods. When you have this car crash, that basically will create an impulse motion at a very short time periods, where these impulse or momentum methods become very useful to be used to analyze the motions that related to these vehicles. Here we can say that in analyzing the kinetics of particles, besides the Newton's second laws methods, we have the work and energy methods as well as the impulse or momentum methods. So recap back, previously The problems we are dealing with, the motions of particles, are through the use of the equation of motions of Newton's second laws, summation of F equal to ma. And this current chapter itself, we introduce two additional methods of analysis. First, the methods of work and energies. The second one will be the methods of impulse or momentums. But on today's lectures, our focus will be on the methods of work and energies. As I mentioned earlier, in using the work and energy methods, we do not really need the information of accelerations. Work and energy methods directly relates the force, mass, velocity, and displacement, whereas the methods of impulse or momentum directly relates the force, mass, velocity, and times. Comparing these with the Newton's second law methods, it relates the force, mass, and accelerations. So these are the differences between the three principles that can be used to analyze the kinetics of particles. So if we are given forces and accelerations, then the best approach or principle to be used to analyze the kinetics of particles will be the Newton's second laws that we have learned in our last topics. The equation will be the summation F equal to ma. In the case of the velocities and displacement informations are available, then preferably work energy methods could be used. The equations in general is equals to T1 plus U1 to 2 equals to T2, where the T1 and T2 is the kinetic energies. The U1 to 2 will be the work of a force. Of course, under the conservations of energy principles, right? We can replace this later on, the U1 over 2, the work of a force, with the potential energies. So later on, we will look into how we make use of these work and energy methods in solving problems that related to the kinetics of particles, particularly when the informations of velocities and displacements are available. In the case of the velocities and times of the particles are available, or we would want to determine these informations, we could utilize the impulse and momentum methods. In the impulse and momentum methods, it built the relationship between the linear momentums, mv, as well as the impulse. So through these relationships, we can determine, like the example that we have discussed earlier, the car crash, and the velocities of the vehicles when they have the crash or impulse at that short periods of time. We will revisit these impulse and momentum methods or principles in our next topics, and today we will focus more on the work and energy methods. Work of a force. If we consider a particle A move to the neighboring point A primes, where the R denotes the positions vectors corresponding to this point A, and these small vectors joining A to A primes can be denoted by the differential dr. And this vector dr, we call it a displacement of the particles. And if we assume that a force F is acting on the particle itself, then the work of the force F corresponding to the displacement dr is defined as the quantity du equals to F dot dr. It's actually the scalar products of the force F and the displacement dr. If the angle alpha is formed by this vector force F and the displacement dr, then the scalar products of the two vectors can be written as F ds cos alpha. We can also express the work du in terms of rectangular components of the force and the displacement. So equals to Fx dx plus Fy dy plus Fz dz. It's not that work is a scalar quantity, so it has magnitudes and sign, but not directions. We also note that work should be expressed in units obtained by multiplying units of length by the unit of force. So if you are using US customary units, then it should be expressed in feet pound. Or if SI unit is used, then it should be expressed in terms of Newton meter. And it is equivalent to 1 joule. So in US customary unit, 1 feet pound is equals to 1.356 joule. If the force F has the same directions as the dr, the work du reduced to F ds. If F has a direction opposite to that of dr, the work is reduced to du equals to negative F ds. If the force F is perpendicular to dr, the displacement, then we have this cos alpha equals to 90 equal to 0, then the work du will become 0. The work of force F during a finite displacement of the particle from A1 to A2 can be obtained using the equations F dot dr by integrating it along the path described by the particles. In this case, is A1 to A2. So it can be shown here. The work of a force from position 1 to 2 will be the integrations of the equations F dot dr from A1 to A2. The scalar product F dot dr can be also represented by F cos alpha ds that we have discussed earlier. And this F cos alpha is represented as the tangential components Ft of the force. So it can be simplified to the tangential component of the force, which is this one along the curve. Taking the integral of Ft ds from the S1 to S2, then basically it will give us the work of a force from position 1 to position 2. And if we plot the curve by Ft against S, then the area under this particular curve will be the work of a force from 1 to 2, position 1 to position 2. And when the force F is defined by its rectangular components, then it can be also represented. This work of a force during a finite displacement can also be represented as shown here. When the particle moving in a straight line is acted upon by a force F of a constant magnitudes and a constant directions, then the work of a force in this case is represented by this one, F cos alpha delta x from A1 to A2. The work of a weight W of a bodies, or the work of a force of gravities exerted on that body, can be obtained by substituting the W in our earlier equations, F ds in the rectangular components. So in this particular case, we have our Fx equal to 0 Fy equals to negative W going downwards, and Fz equal to 0. So the equation can be rewritten as du equals to negative W dy. So the work of a force from one position to another position 2 will be equals to negative the integral of W dy from y1 to y2. Or we can return it as negative W y2 minus y1 or negative W delta y. Work of the weights is equal to the products of the weights W and the vertical displacement delta y. So in the case of the bodies is moving from y1s upwards to y2s, where your y2 is larger than y1, then we are saying that the work is negative. So in the figures above, will the work done by the weight become positive? The answer is yes. When the body is moving from downwards from y2 to y1s, where your delta y is less than 0 or negative, then you will have a positive work. Next, work of a force exerted by a springs. Consider a body A attached to a fixed point B by a springs, and it is assumed that the spring is undeformed when the block is at A naught. And experimental evidence already shown to us that the magnitude of force F exerted by the spring on the body A is proportional to the deflection X. So that here we have this F equal to Kx and K is equal to spring constants. To determine the work of a force exerted by a springs during a finite displacement of the body from A1s to A2, where your A1, when your x equal to x1, A2 is x equal to x2, we can then apply what we have learned earlier, du equals to F dot dr. But in this case, the force has a directions opposites to the displacement dr. So we will be using du equals to negative F ds, and in this particular case is negative F dx. So substitute the F equals to Kx, then we have du equals to negative Kx dx. To find the work of the force exerted by the springs when it is extended from A1 to A2, so u1 to 2 will be the integral of this Kx dx from x1 to x2 with the negative sign at the front here. Then it will give us the work of the force u1 to 2 is 1 over 2 kx1 square minus 1 over 2 kx2 square. So in this case, when the body is extended from A1 to A2, then we have our A2 is larger than A1, or what we call the x2 is larger than x1, then we will have a negative work of the force. When this body is returning to its original undeformed positions, then we have our x2 is less than x1 in this case, which is the final displacements will be x2 is become less than our initial displacement x1 at here to here. Then substitute to these equations work or force exerted by the springs, then we will have a positive work where x1 here is larger than x2 in this case. So it will give us a positive work. And when the spring or the body itself is deformed towards these directions, or what we said, when the body is, or the spring is being compressed from its undeformed positions, we will have our work of the force exerted by the spring U1 to 2 will be equals to this one negative will be replaced, will be removed, then will become integrations of kx dx from x1 over x2. And in that case, our work of a force exerted by the spring when it is being compressed will equals to 1 over 2 kx2 square minus 1 over 2 kx1 square. So it's a slightly difference. So in the case of it is being compressed, where you have your initial length of the spring is larger than your x1's initial length of your spring is larger than your x2, the final position when it is being compressed, then you have so-called the negative work when it is being compressed. So in the case of the spring, or the compressed spring is returns to its original undeformed positions in this case, then we will have our final x2 positions is larger than our x1 positions. Then substitute into that equation back, u1 to 2 equals to 1 over 2 kx2 square minus 1 over 2 kx1 square. Then we will have a positive work in this case. In the case of it plots the graph F versus X, the work of a force exerted by the springs is equals to the negative areas under the curve F against X. So in other words, U1 over 2 we can rewritten as using the area of trapezoid equals to 1 over 2 f1 plus f2 multiplied with this delta x, which is from x1 to x2. To summarize in words on work of force, right? First, we are looking into the work or force of gravities exerted on that body, or what we call work of the weights of the bodies. Right, so here if we are having a work of a force of gravities, we know that it is equals to u1 to 2 equals to negative w, which is the weight, y2 to y1. So to summarize it, when the body itself is going up, when it is moving upwards, then we have our y2 larger than y1. Then we are saying that it's the work of force of the gravity, or work of force of the weight of the body is producing a negative work. So in the other case, when it is moving downwards, then in this case we have our y1 initials is larger than our y2 final. Then if you substitute into here, we will have the work of a force of the gravity is a positive work. Next, we also learn work of a force exerted by a springs. So work of a force exerted by a spring. Then we understand that when it is undergoing an extended, so the work of a force of this spring from 1 to position 2 will be 1 over 2 k x1 square minus x2 square. So when the spring is extended, so if it is extended, then our x2, the final one, will be larger than the initial ones. Then here we will have a negative work. When the spring, the extended spring, is returned back to its undeformed positions, then here we will have our initials is larger than the final. Then substitute to the equations here, the work or force equation here, then we will have a positive work. So here we have equals. The number of forces frequently encountered in problems of kinetics do not work. They are forces applied to fixed point where you have this ds equal to 0, or acting in directions perpendicular to the displacements when you have this cos alpha, which is 90 degree, equal to 0. So in these cases, the force, we are saying that it do not work. So these are the examples of when forces do not work. So for example, the reactions at frictionless pin supporting the rotating bodies, the reactions at a frictionless surface when body in contact move along surface, reactions at a roller moving along its track, and the weight of a body when its center of gravity move horizontally. So that is when the case cos alpha equal to 0, the rest will be ds equal to 0. Next, the kinetics energy of particles and how we derive the principle of work and energies. We consider particles of mass m act upon by a force F and moving along a path which either rectilinear or curvilinear. And if we express the Newton's second laws in terms of the tangential components of the forces as well as the accelerations, tangential accelerations, Ft equals to mat. Ft equals to mat. Then we can actually derive this at or tangential acceleration as equals m dv dt. And this dv dt under the differentiation rules, we can return it as dv ds dt. So ds dt is the velocity mv. So we will have this mv dv ds. And we rearrange it, we will have this ft ds equals to mv dv. So if we integrate this from a1 to a2, then we will have from the position S1 to S2 ftds, the integrations of ftds equals to m, which is a constant, then v dv, the integration of v dv from v1 to v2. And remember that these terms on the left is the work of a force, u1 to 2, and the integrations of v dv basically give us the v square over 2. So giving us 1 over 2 mv2 square minus 1 over 2 mv1 square. And this 1 over 2 mv square can be represented as T, and we call this as kinetic energies. So the principle of work and energy, in other words, can be written as u1 to 2 work of a force is equals to the change of the kinetic energies, T2 minus T1. So here the work of the force F is equal to the change in kinetic energy of the particles. And the unit of work and the kinetic energy remain the same, right? Which is joule or Newton meter in SI units. The work U1 to 2 is a scalar quantity, so the expressions 1 over 2 mv square, which is the kinetic energy, is also a scalar quantity. So under the principle of work and energies, we can rearrange this as T1 plus U1 to 2 equals to T2 also. So what it means here, the kinetic energy of a particle at A2 can be obtained by adding to its kinetic energy at A1 and the work done during the displacement from A1 to A2 by the force F exerted on the particles. So T2 can be obtained by adding T1, which is the initial kinetic energy, plus the work of a force or work done by the particles moving from A1 to A2. The applications of the principles of work and energy greatly simplifies the solutions of many engineering problems, which involve forces, displacement, and velocities. If we consider, for example, the pendulums OA as shown here, which consists of a bob A and a weight W attached to a cord with the length of L. The pendulum is released with no initial velocity from the horizontal position OA1 set here and allowed to swing in a vertical planes. We wish to determine the speed of the bob as it passes through A2 at here, directly under the O. We can first determine the work done during the displacement from A1 to A2 by the force acting on the bobs. We can draw a free body diagrams of the bobs as shown here, showing the actual forces acting on it. We have the weight W and the force P exerted by the cords. And we know that this force P does not work because it's normal to the path. Only the force which does work is the weight W. So moving downwards, we know that it's moving downwards with the vertical displacement of L from A1 to A2, which is the L. And it's moving downwards, and we know that the work is positive, which is equals to WL. U1 to 2 equals to WL. And now we consider the kinetic energy of the bob. Initially, at A1 is at rest, so we find that the T1 or the kinetic energy at the initial condition is equal to 0. Whereas the T2, the kinetic energy at position number 2, here is equals to 1 over 2 mv2 square, where our m is equals to W over G. So based on the work and energy principles, as we have derived just now, T1 plus U1 to 2 equals to T2. Then we have T1 equal to 0, U1 to 2 equals to WL. T2 is 1 over 2 m V2 square, which is equals to 1 over 2 W over G V2 square. And from there, we can find the velocities at the position number 2, V2 equals to surds, or square root of 2GL. And you can see that the velocities is found without determining the expressions for accelerations and integratings. All quantities are scalars and can be added directly. So for those forces which do not work, are eliminated from the problems. So it becomes easier when we are dealing with problems that involving forces, displacement, and velocities. However, the work energy methods have its limitations. For instance, the method of work energy cannot be used to directly determine an accelerations. In determining a force which is normal to the path of the particles, a force which does not work, for example, this P, the method of work energy must be supplemented by the direct applications of Newton's second laws. Or for examples, in calculating the tension in the cords of these pendulums, we need to draw a free body diagrams together with the expressions of Newton's second laws in terms of tangential and normal components before we can solve for the accelerations, the tensions of the bob informations. So here we know that at A2 we know the velocity V2 is equals to surds 2GL, and making use of the free body diagram and the kinetic diagram itself, we come up with Newton's second law summation of Fn equals to MAN. So we know that the tension of the cord itself, P minus W, equals to what we call the MAN, right? When the AN, the normal accelerations, is equals to V squared over R, which is V squared over L. So by doing so, rearrange it, then we have, or we can determine the tension of the cords, P equals to 3W. Next, power and efficiencies. Power is defined as the time rate at which work is done. So power is equals to du dt, and we know that the du is F dot dr. So the power is F dot dr dt, and dr dt is the velocity. So we can also determine our power as F dot v, the dot product of the force and the velocities. The dimensions of power are work over times, or force times velocities. And the units of power is watts, is equals to 1 joule over seconds, or 1 Newton meter over seconds. Or in the units of horsepower, and 1 horsepower equals to 746 watt, or in US customary unit is 550 feet-pound over seconds. The mechanical efficiencies of a machine was defined as the ratios of output work to the input work. This definition is based on the assumptions that the work is done at a constant rate, So the ratio of the output to the input work is therefore equals to the ratio of the rates at which the output and input work are done. So we could have also expressed the efficiencies as the power outputs over power inputs. Potential energies. If the work of a force only depends on the differences in positions, then we can express this work as potential energies. This can be demonstrated as in the examples here. When the roller coasters at the tops of the peaks here, the potential energy is stored and it will be transferred to the kinetic energy as the cars descends. In other examples, the elastic potential energy stored in the trampolines will be transferred to the kinetic energy and the gravitational potential energy as the girl flies upwards. If we consider again a body of weight W, which move along a curved path from point A1 of the elevations of Y1s to a point A2 with the elevations Y2s. And we recall that the work of the force of the gravities, W, during this displacement is U1 to 2 equals to W Y1 minus W Y2, or negative W Y2 minus Y1. This work of force of gravities is independence of path followed. It depends only on the initial and final value of Wy, the initials and the finals. So this function is called the potential energy of the body with respect to the force of gravity W, and is denoted by Vg. Here, Vg equals to Wy equals to the potential energy of the body with respect to the force of gravity. We can also say that U1 to 2, the work of force of gravities, is equals to the initial potential energy minus the final potential energies. The choice of datums from which the elevations y is measured is arbitrary. It can be any randoms. Unit of the work and potential energy are the same also, in which your Vg equals to Wy and the unit is in joule or Newton meter, Nm. And if we now consider a body attached to a spring and moving from a position A1 corresponding to a deflection x1 of the springs to a position A2 corresponding to a deflection x2 of the springs, and the work of the force F exerted by the spring of the bodies is defined as U1 to 2 equals to 1 over 2 kx1 square minus 1 over 2 kx2 square. And you can see that the work of the elastic force is just subtracting the value of the functions 1 over 2 kx square corresponding to the second positions of the body from its value corresponding to the first positions. So these functions is denoted by VE and is called as the potential energies of the body with respect to the elastic force. Here, work of a force exerted by a spring, or we call it a work of a elastic force U1 to 2, is equals to the potential energy of the body with respect to this elastic force, the initials minus the finals. Recall what we have learned earlier. When the spring is ascended from the A1 to the position of A2, the work of a force exerted by the spring on the body is negative. And here we can say that the potential energy VE increases. And we should note that the expressions obtaining VE is valid only if the deflections of the spring is measured from its undeformed positions. Here, to find the work of a force, which is the area under the curve F versus X. So we are using the initials potential energies, which is these small triangles, right? And also the final so-called potentials energy, which is the large triangles. Finding the difference between the initials and the finals, we will have the work of a force exerted by the springs, which is a negative work. Work of a force of a weight of a particles and the work of a force exerted by the springs, they are conservative forces, and they can be expressed as a change in potential energies. So we learned before the V, G, and VE, the potential energies of the weight of a particles and the potential energy of the elastic force. When we are finding the change of this potential energy, we find the work of the force. So they are so-called conservative forces. When a particle moves under the actions of conservative forces, the principle of work and energies can be expressed in the modified forms. So the U1 to 2, previously from the concept of work and energies, is equal to T2 minus T1, and under the conservative force, the U1 to 2 is equals to V1 minus V2, whether is Vg, the potential energies of the weights, or Ve, the potential energy of elastic force. Follow that, then we will have T1 plus V1 equals to T2 plus V2. So this indicates that when a particle moves under the action of conservative forces, the sum of kinetic energies and the potential energy of the particles remain constants. And the sum T plus V is equals to the total mechanical energies denoted by E. So here the total mechanical energy is constant when it's moved under the action of conservative forces. We consider back the examples of the pendulums, which is released with no velocities from A1s at here and allowed to swing in the vertical planes. And if you measure the potential energy from the level A2, which is our datums, our reference, then we have at A1s, we have the T1, which is the kinetic energy equal to 0, and our V1, which is equals to the potential energy of the weight equals to WL. Then T1 plus V1 here is equal to WL. When the bob reach A2, we have our kinetic energy T2 equals to 1 over 2 mv2 square, which is equals to 1 over 2 W over G, where the V2 is V2 square is a 2GL. Then we have T2 equals to WL. And in this case, the potential energy of the weight is 0 because the datums is at A2. So no change in the positions, then V2 is 0. Then end up our T2 plus V2 also equals to WL. So it is proven that the mechanical energies where we have this T1 plus V1 equals to T2 plus V2, which is constant. This is what we call the conservation of energies principles. It's not that the friction forces are not conservative, so there will be a loss due to. It is noted that the friction forces are not conservative forces. In other words, the work of a friction force cannot be expressed as a change in potential energies. The work of a friction force, as we noted, is always negative. So when a mechanical system involves frictions, its total mechanical energy does not remain constant, but decreases. The energy of the systems, however, is not lost, but is transformed into other types of energies, for example, heat, and the sum of the mechanical energies and the thermal energy, in this case, will remain constant. So total energy is still remain constant. That basically gives us a principle of conservation of energies.